Welcome back to Programming Problems. Today, we'll have a look at Clumsy Crucible from Advent of Code 2023. Let's start. We helped the elves to get lava flowing, but it's not getting to where it needs to go fast enough. As a solution, the elves start loading up crucibles on wheels. The crucibles are used to navigate a city, but it cannot travel in straight lines for too long due to stability issues. On top of that, every city block that is traveled through will cause the lava in the crucible to lose some heat. We're provided a 2D map indicating how much heat loss every city block causes, and the crucible can at most travel 3 city blocks in a straight line before it must turn 90 degrees. You can never reverse direction. Given the constraints of the problem, what is the minimal heat loss that we can experience while traveling from the top left corner to the bottom right corner of the map? Here is an example city map where we will start in the top left corner. Note that the heat from the first city block does not count towards our heat loss, unless we visit that corner again at a later stage in our path. This path then is one of possible multiple minimal paths, where the heat loss is minimized. The total heat loss is 102. Do you see how we never travel in a straight line for more than 3 steps? Let's jump into today's solution. The problem asks us to navigate a grid where there is some cost associated with every step along our path. This then smells like Dijkstra. Of course, there are some additional constraints, but the pseudocode for that algorithm is as follows. Given a graph and a source vertex to depart from, every vertex gets its distance from the source set to infinity. Then the vertex is added to the queue. Next up, we first set the distance from the source to the source itself to 0. Then, while the queue is not empty, we take vertex u, which is the vertex with the lowest distance in the queue, and we remove it. Then, for all neighbors of that vertex, we update the shortest distances. A critical aspect of this algorithm is getting the vertex in queue with minimal distance. We can achieve this behavior trivially by using a so-called priority queue. This type of queue allows us to always have access to elements in the queue which are sorted to some property. In the case of Dijkstra, we're interested in the shortest distance. In our case, we're interested in the least amount of heat loss. Because somewhat informally, we can say that the first time we visit any node in the algorithm is via the shortest or cheapest route to that specific node. Suppose this was not the case. Then there is a better path that's shorter or cheaper, which we skipped over with our priority queue. However, the priority queue always gives us the shortest or cheapest paths first. So we know that every time we visit a given node from our queue, that it's the cheapest route towards that node. In the example on the left, you could say that all blue nodes are already visited, and the pink nodes are in our priority queue. Which node would we visit first? Well, we would pick the node with the smallest value, in this case the node with value 3. Because we use the priority queue, we can add neighbors of any position in the map more creatively to our queue. Typically, we would only explore neighbors which directly touch. However, in this problem, we can look ahead and thereby satisfy the straight line property more easily. So suppose we're currently exploring the blue position and we're traveling east. Then instead of taking 1 step forward, 1 to the left, and 1 to the right, we can just add all 3 steps to the left and all 3 steps to the right to our priority queue. This way, we don't have to keep track of the distance as part of our current path to see if we are even allowed to take an additional step forward. Suppose on the next step, the cheapest node in our priority queue is the one below. Then we add these 6 additional states to the queue. The outline of the solution then looks as follows. First, we parse the data and mark the target position, after which we just compute the minimal heat loss using our modified Dijkstra's algorithm. The algorithm looks as follows. Note first at the top that we're using heap queue from the standard Python libraries as our solution for a priority queue. Then we're adding 2 initial states to the queue. The first value in both states represents the heat loss, since that is the main property that we want to sort on. The second is the position in the map as a tuple. The third property of the state is the direction in which is being traveled, which is also a simple 2D vector as seen on earlier days. Of course, we start on the top left corner, 0, 0, with 0 heat loss, and we can travel either down or right. All visited states can be tracked in a set, so we don't iterate over states that we've already explored before. Then, while the priority queue is not empty, we iterate. First, we get the lowest cost path or state from the queue, and we'll extract the heat loss, the position, and its direction. Then, if the position and direction pair is already visited before, Then by the invariant which we've discussed before, there is no way that this path can be cheaper, so we skip it. If we did not see it, we add the state to our visited set. Another exit from our loop is when our position equals the target position. Again, from our invariant, we know that the first time that we'll be here, the heat loss from that state is minimal, so we can just return the value. Otherwise, we still need to continue the exploration of the map. For every state in the reachable states, we'll just expand the priority queue. The magic then, of course, is in getting these reachable states. Let's have a look. As seen at the start of this segment, we'll get lines of states. At the top, given a position, direction, and the amount of heat loss from the source state, we can get a line of states after rotating our current direction to the left, and once after rotating our current direction to the right. Getting a line of states simply means that we get a line of positions, which is a more trivial problem, and then making sure that every position has the appropriate heat loss associated with it, turning it into a proper state to use in our priority queue. The line of positions is just looking 3 positions ahead in the given direction, and only returning those positions that are actually inside of the grid. Lastly, to make interaction with the tuples a bit easier to understand, I opted to make 2 2D vector types, which are basically just tuples of integers. Updating a position is then as simply as adding the direction to the position as shown here. If we're dealing with directional vectors such as east or south on the previous slide, then rotating left or right is also very straightforward. You just swap the x and y coordinates and flip a sign. If this is not intuitive to you, please take a moment to see why this works in our context by analyzing the code and the diagram. And that was it already. You should now have all the means to solve part 1. Let's go to part 2. In a desperate attempt to scale up their operation, the elves upgrade to even larger crucibles. The downside is that these crucibles are even harder to steer. Once it starts moving in a given direction, it must move a minimum of 4 blocks in that same direction before it can turn. The crucible can move at most 10 consecutive blocks without turning. Given these new rules, what is the least amount of heat loss that can occur? Here's the example map from part 1 again, and here's a new minimal route that can be taken. The total heat loss is 94. Do you see that every straight edge of the path is between 4 and 10 steps long? Let's look at the solution. As for part 1, we'll apply the same algorithm, but the subsequent states that follow from a given state are now between 4 and 10 positions away. In this diagram, I show you steps that are at least 3 positions away. The point is that for a given blue state, you don't have to add all the states. It is fine to just skip a few. The logic for getting the next states can be completely arbitrary. We could even have a checkerboard pattern if the problem were to ask for it. In this case, however, we just care about the states that are between 4 and 10 positions removed, on the left and the right, from the current state. The only part of the algorithm that then needs to change is the line of states and the line of positions. Here we keep the line of positions fairly simple. It just returns a line of 10 positions in the grid. The line of states does the filtering to see if a state is at least 4 positions away, and it of course makes sure that the heat values are updated, thereby converting the positions into actual states for our algorithm. Thank you for following along. This was it. You should now be able to get 2 additional stars. Don't forget to like and subscribe for more content like this, and see you next time.